In last video, we have introduced the outliers. Here is the formal definition of outliers. So in histogram, if you find an isolated bar, it implies that the existence of outlier. A numerical summary of the observation is called resistant if extreme observations have little, if any, influence on its value. So resistant is a good property. We want our numerical summary to have this good property. We use measures of a center to answer this question. What is a typical value of the observation? There are three different measurements of center we will study: mean, median, and mode. Here is the definition of mean, a balance point in a set of data, in another name average. Here is the formula to find the mean. This is called X bar. It is the sample mean. And this notation is called mu, is the population mean. Sample mean doesn't have to be equal to population mean. Sometimes sample mean equals population mean. Sometimes they do not equal to each other. And this is called sigma x. It is the summation of all x values. For bell-shaped unimodal distribution, the mean usually locates at the center of the histogram. For the skew to right histogram, usually you can find the mean at the left part of the histogram. For skew to left histogram, usually the mean will locate at the right part of the histogram. Because the mean use all values, including the very small and very large numbers, mean is affected by outliers, and all values in the dataset play an equal role. Overall, this means mean is not resistant. This is an example about how to calculate sample mean, or in another name, X bar. X bar or sample. First, we want to add all numbers from the data set, or in another name, sigma x. 13 from here, 14 from here, and so on and so forth. And the summation of all those numbers, all 12 numbers, is 231. The 12 equals to the number of data set, or how many data you have. We have 12 data here. So the X bar is equals to 231 divided by 12. This is how we calculate X bar. The average number of points scored by the USC football team in 2016 was 19.25 points. Is the interpretation of X bar, or sample mean here. In this example, we will change number 44 to 88. So this number here was 44. Now we change it to 88. The sample mean is still calculated as sigma x divided by n. Sigma x is 275. It is calculated as 13 plus 14 plus everything else plus 88 plus 7. You can verify this calculation by yourself. N here is still the number of data, or number of observations. Now the new sample mean is 22.92. It was 19.25. So you'll notice that the higher value causes the mean to increase. This example illustrates that the mean is not resistant to extreme values, or we say outliers. Extremely high or low value will affect the mean. Specifically, the higher value causes the mean to increase. Here is the formal definition of a median. Median value when data is ordered from the smallest to largest. Half of the value are less than or equal to the median. Half the values are greater than or equal to the median. Here is how you can find median. This is the first step. You want to order the data from the smaller to the larger, or larger to the smaller. Both order work. Second step is determine if the sample size is even or odd. If it is even, then the middle number falls between two numbers. The middle number of a data set between the n divided by 2 and the n divided by 2 plus 1 position. The average value at those two positions to get the median. This two position means n divided by 2 and n divided by 2 plus 1. If the sample size is odd, then the middle number falls at a particular value. The middle of the data set falls at the n plus 1 divided by 2 position. The median is the value at this position. Does median affect by outliers? The answer is no. Extreme values are not used in the calculation of the middle number. Median is resistant. This is an example about how to calculate median. We have 12 data here, and as we know, 12 is even. So the next thing we want to do is we find the n divided by 2 position and then n divided by 2 plus 1 position. The 12 divided by 2 is 6, and the 12 divided by 2 plus 1 is 7. Note that the data is placed from smaller. This is the smallest one to the largest one. And this is the first position, second, third, and so on and so forth. Now we find the 6th and the 7th position, and we should average the numbers that fall in those positions. So this is the 6th position and 7th position, and we just use 14 times 14 divided by 2, which is still 14. This is the appropriate interpretation about the median. The USC football team scored 14 or fewer points 50% of the time, and 14 or more points 50% of the time. This example can explain why median is resistant. Note that now in this data set, the largest number is 88. It was 44. However, we use the same methods to calculate the median. So first, we place the data from small to large, and we still find is a 6th and 7th position. So this is the 6th position, this is the 7th position, and the median is still 14. Right. So no matter how we change the maximum value or extreme values here, the median will not change. So we have the conclusion that the median is resistant. The outlier here is 88. Did not affect the median. The mode is the value that appears most frequently in a data set. It is the only option for categorical variable. mode can be used for quantitative variables as well. Is mode affected by outliers? The answer is no. Mode is resistant. This is an example about how to find mode in a series of data. For example, this series, as we can see, 7 appears 4 times. So this is the first time, 7th time, 3rd time, and 4th time. And the number 5 also happens, appears 5 times, 4 times. I'm sorry, 1, 2, 3, 4. So for this series of numbers, we have 2 modes. It's 5 or 7. Mode doesn't have to be unique. And this is the second example, length of time. We find the number that appears most frequently. As I can see, the number 3.33 happened once and twice. And at the same time, the number 3.20 happened twice. 1, 2. So the mode for this series of number is 3.33 or 3.20. And this is a last example about the conference versus out-of-conference games. C stands for conference. O stands for out-of-conference. This result is straightforward because the conference game happens 1, 2, 3, 4, 5, 6, 7, 8. The conference games appear 8 times. Meanwhile, the out-of-conference game only happens 1, 2, 3, 4 times. So that's how we can tell conference games is the mode. Comparing the mean and the median. The shape of distribution influences whether the mean is larger or smaller than the median. If the distribution is perfectly symmetric, then the median will equal mean. If the distribution is skewed to left, mean will be smaller than median. If the distribution is skewed to right, the mean will be larger than median. The more highly skewed the distribution is, the more the mean and the median tend to differ. Example 12. From last video, we have learned how to determine whether a distribution is left skewed or right skewed. This one is left skewed. Different from what I have teach you in last video. This is another method we can use to determine whether it's left skewed or not. If it's left skewed, the left tail is longer from the peak than the right tail. So this is the peak, right? And the distance between the left tail to the peak is this distance. And this one is longer than the distance between the right tail to the peak. This is shorter. And the median will, from the actual data set, we know the mean is 6 and the median is 6.5, and the 6 is smaller than 6.5. That's how we can have the conclusion. And it is obvious that this dot plot shows us the distribution is symmetric. And for symmetric distribution, the mean should equal median. And from the actual data set, we have that the sample mean is 5, and the sample median is also 5. In this example, I'll show you how to read stem and leaf plot. First, I'll show you how to get the minimum value here. As we learned from the last video, we will get the number from the stem. And the smallest stem number is 10, and we times 10 by the stem unit 0.1, and we plus the smallest leaf number, which is 0, and we times the leaf unit 0.01. We still have 1. That's how we have the minimum value, or 1.00. To find the maximum value, first we need to find the maximum stamp number, which is 15, and we times 0.1, which is the stamp unit, and we plus the largest leaf number, which is 9. We use 9 times 0.01, and the summation is 1.59. You can verify it by yourself. This histogram, this stem and leaf plot is right skewed. As we can see, this should be the peak. This should be the peak, and this part is what we call the right tail. So this is the right tail. Right tail is longer than the peak from the left tail. And you can verify by yourself. Since we have all the data we need, the mean of this sample, or the mean of all those numbers, is 1.22, and the median is 1.18, and the mean is larger than the median. So we have 3 measurements of center: mean, median, mode. Which one should we use? Here's some 2 general rules we can follow. If the distribution is highly skewed, then the median is usually preferred over the mean, because it better represents what is typical. If the distribution is only mildly skewed, then the median is usually preferred, because it yields the numerical value of all observations.